So why is nanostructuring important? I don't think you can read this from the back, so let me just say that there is a rationale. It's to do with the phonon scattering spectrum, and essentially the answer is the thermal conductivity decreases with the microstructural scale. Make the microstructural scale smaller. That might be the grain size, maybe the superlattice spacing, maybe a precipitate size. Then you can decrease the thermal conductivity. Consequently, ZT goes up. And there are different ways of describing this. So this is a typical nanostructured material on the right-hand side. It's a TM picture. These are grains around 10, 20 nanometers in size. This is strontium titanate material. And the reason these have low thermal conductivity is that imagine the heat is going from left to right in this image. I'll show it schematically here. The heat flux has to go through the grains, then across the grain boundaries, then across the grains, across the grain boundaries. So you have a whole series of interfaces that the heat has to propagate through. That means, very crudely, that the temperature versus distance will be linear inside the grains, and then there'll be a big temperature drop, big being relative, at the grain boundaries. So you can see you have this type of behavior. So it turns out the larger the number of interfaces per unit length, the lower the thermal conductivity. And that's expressed by this equation, which, in the interests of clarity, I won't describe. And the essential point is that in polycrystalline material, the thermal conductivity is the sum of the conductivity of the grains plus the ones of the grain boundaries. So you want as many interfaces as possible. So that's why many of those points with high ZT have high ZT, because people have made them in very small grain sizes. So in the ceramics community and the physics community, they've used things like spark plasma sintering, or they've used precipitation hardening, and various other ways. This was not exactly a new development, but what was new is people were able to now produce what I call synthetic superlattices. In other words, they had to grow them atom by atom, typically by MBE or CVD processes. And this is an example. I'm sorry, I forgot the attribution. This is thermal conductivity, the silicon germanium superlattice. This is from 0 to 20 watts per meter Kelvin as a function of temperature. These all have the same composition, but as you make the superlattice spacing smaller and smaller, then the thermal conductivity goes down. This is a very successful process for lowering thermal conductivity, but it's expensive. You have to use MBE techniques. And unfortunately, these sort of structures don't persist at high temperatures. So it turns out that this problem with nanostructuring is they're not stable against diffusion. So this is what I call the Achilles heel of nanostructuring. So if you want something to last at high temperature over a long period of time, you either have to stop diffusion, or you have to have something that's completely resistant. So what diffusion does is it causes microstructures to coarsen, so-called Austral ripening process. It's a thermally activated process, and really all it means is that atoms will go to a more favorable position as a result of thermal activation. So all the equations are this form of rate equation. There's an activation energy divided by RT, and then you can manipulate this to give you a lifetime parameter. It's called in the metallurgical literature, this is the Larson-Miller parameter. It's basically the product of temperature times a constant, which has to be determined, plus log of T time. So ideally, you want this term to be very low. But you can't, because it goes up as log T, and it goes in proportion to temperature. So the conclusion that you have to make, if you're interested in a something that's going to last 5, 10 years as an energy source with no maintenance, is you cannot rely on existing nanostructuring approaches. And just to give you some evidence of that, some of you may believe very strongly that making synthetic superlattices is very attractive and is the way to go. Let me show you some data. This is silicon germanium superlattice. Unfortunately, you can't really see all the superlattices inside of here as well. This is as grown, 20 minutes at 850 degrees centigrade, 20 minutes at 1,000 degrees. By 1,000 degrees, all the superlattices are dissolved. And you can see that in terms of the X-ray scattering. As grown, you see these periodic oscillations, which are telling you have this periodic structure, the nanostructuring. And with time, you see this intensity scattering regime becomes flat, smoother and smoother. So these oscillations are dying away. It's rather regrettable that this was published in 2015 when this was also known 20 years ago, but never mind. Do the old thing in the new field and you can publish it. Actually, to be fair, the old work didn't include the X-ray scattering. So this, I'm not using this in any other sense, really, than to say that high temperatures, these nanostructures that are produced by synthetic processes, are not stable.